Hello everyone, and welcome to today's webinar entitled Transportation Asset Risk Assessment, Climate Risk Assessment Tools and Frameworks for the Transportation Sector. My name is Sophie Donahue, and I will be moderating today's webinar. I'm a research officer with the Transport Canada Transportation Asset Risk Assessment Initiative, otherwise known as TARA. Our broader team at Transport Canada hosts a webinar series called Transportation, Adapting to the Changing Climate. For those of you who are new to today's webinar series, the objective is to build knowledge and capacity both within Transport Canada and the broader Canadian transportation sector on the impacts of a changing climate and adaptation solutions. Today's webinar will showcase how established climate risk assessment tools and frameworks have been put into practice by 3 TARA-funded projects and how the tools and frameworks were adapted in order to facilitate decision-making and incorporate climate risks into the project's business practices. Before we get started, I would like to cover some administrative details. If you run into audio or technical issues during the webinar, please click on Participants icon at the bottom of your screen, hover over Suzanne's ceiling, select More, and go to Chat. Please note that your lines have automatically been muted to avoid any audio distractions or feedback during the webinar. There will be a dedicated Q&A session at the end of the webinar, but that does not mean you have to hold your questions until then. Please feel free to type out your questions during the presentation in the chat function, which can be found at the bottom besides participants. Today's webinar is being recorded, and a link will be sent out afterwards to everyone who has participated. Furthermore, while today's webinar will only be available in English, French copies of the slides will be circulated afterwards. Now, without further ado, I would like to introduce today's speakers. First off, we'll have a short presentation from my colleague Michael Dodlin, who is a policy analyst with the TARA team here at Transport Canada. Michael will be providing a short overview of the TARA initiative, and after his presentation, we will hear from representatives of the 3 TARA-funded projects. The first presentation will be given by Gary St. Michel, who will be presenting on behalf of Public Services and Procurement Canada. As the technical lead for Tetra Tech's Vancouver Asset Management Group, Gary provides expertise in specialized engineering consulting in the preservation of existing infrastructure through the use of innovative rehabilitation technologies, long-range planning, and advanced life cycle cost-benefit analysis methods and asset management systems. Our second presentation will be delivered by Vincent Lades, who is presenting on behalf of Transport Canada's Atlantic region. Vincent is a senior coastal engineer with CBCL. Over the last 20 years, he has completed a wide range of infrastructure projects throughout Atlantic Canada's diverse coastal communities, waterfronts, and harbors. His work involves a science-based collaborative approach towards functional solutions to deal with dynamic coastal processes and climate change risks. Vincent has led many TARA-funded climate change risk assessments on key federal coastal infrastructure in Eastern Canada. And last, but certainly not least, we are joined by Megan Roche, presenting on behalf of Calgary Airport Authority, where she is a climate change and environmental analyst. Megan has a Bachelor's of Science degree in geology from the University of Calgary and has been with the Calgary Airport Authority for the past 5 years. Megan is also a member of the City of Calgary Climate Risk and Adaptation Working Group. On behalf of Transport Canada and today's participants, I'd like to extend a warm welcome to our TARA project representatives presenting today. Now, without further ado, I will turn things over to Michael to get us started.
Thank you very much, Sophie. As you heard, my name is Michael Dodlin, and I'm a Policy Economic Officer on the Climate Change Adaptation and Planning team here at Transport Canada. I've been working on the Transportation Assets Risk Assessment Initiative, or the TARA initiative, for about 1.5 years now, and I'm just going to give a brief presentation providing some background on the initiative, our work to date, and our goals in supporting this webinar. Alexa, next slide, please. Thank you. So I'm sure I don't need to spend too much time explaining to anyone on this call the importance of taking action to address climate change. In brief, the impacts of climate change are being felt right now across the transportation sector, disrupting the movement of people and goods and increasing costs. As the climate continues to change, the intensity of these impacts is expected to increase. My team at Transport Canada is the Climate Change Adaptation and Planning Group. We have partner teams that focus on mitigation, such as finding ways to reduce emissions from the transportation sector, but we focus on adaptation. That is, given the changing climate, how can we help the sector adapt and build resiliency? To this end, we have 3 main lines of work: a policy research group that coordinates adaptation within our department, and 2 funding programs, one focused on adaptation in northern transportation, and my own, the TARA initiative, that works in the assessment of climate risks to federal transportation assets. The mandate of the Terra Initiative is to better understand climate risks to federally owned transportation infrastructure and potential adaptation solutions that could be employed. We are funded with $16.35 million over 5 years, coming out of budget 2017, so we're just wrapping up our fourth of those 5 fiscal years. Our main tool to meet our mandate is providing funding and other supports to partners to conduct climate risk assessments of their assets or subcomponents of climate risk assessment projects like specific impact studies or certain types of instrumentation. We can also support research projects that provide useful knowledge to our assets and have a close relationship with the National Research Council. Next slide, please. Thanks. So where have we had an impact? To date, we've supported projects at 50 transportation assets across Canada, covering airports, ports, highways, bridges, and more in 9 of the 10 provinces. I will note that, as specified in our mandate, these are federally owned assets, but it's really important to us that we share knowledge and lessons learned and encourage collaboration across the entire transportation sector. Next slide, please. Having given an overview of the project work of the Terra Initiative, I just want to quickly outline our goals in supporting and organizing this webinar today. First, we hope to build capacity on the use and understanding of climate risk assessment tools and frameworks. When we talk to our stakeholders, whether they are asset managers or consulting professionals, we frequently hear a desire not only for more knowledge about what tools are available to help understand climate risks, but also for information about how those tools have actually worked when implemented by real assets. We hope to provide some insight on that today. Secondly, we hope that in hearing from those who have carried out projects funded by the initiative, stakeholders of all types can be encouraged and supported in spurring action to understand climate change risks and take adaptive action in the transportation sector. And finally, we hope to help grow peer-to-peer networks to facilitate the exchange of experiences, lessons learned, and best practices. Whether you are a presenter or an attendee, and whether climate adaptation in the transportation sector is your day job or a passing interest, we hope that you can make some connections, even in this virtual environment, with other folks here today, and in doing so, help build a Canadian and global transportation sector that is resilient, efficient, and reliable, even in the face of mounting climate impacts. I will be happy to take any questions on the Terra Initiative at the end of the webinar in the Q&A period, but for now, that's it for me, and I will pass the virtual microphone over to Paul Frame and Gary St. Michel to start off the first presentation. Thank you.
Great, thank you, Michael. My name is Paul Frame, and I'll give you a bit of a brief background on the Alaska Highway for those of you who may not be so familiar, but we've been responsible, Public Works has been responsible for the highway since 1964 for the operations of 835 kilometers between Fort St. John, which is about kilometer 133, to kilometer 968, which takes us to the Yukon border. As custodian of the highway, one of our priorities is looking to gain more understanding of the interaction between climate change and the current infrastructure components along the highway, including 58 bridges and bridge culverts, hundreds and hundreds of small culverts. We have 10 maintenance yards, 6 salt sheds along the route, and various gravel pits as well. So it's important for us to address and plan for climate change impact on the highway infrastructure components, and to look at any significant vulnerabilities as well to allow us to focus current maintenance and capital projects and programs on high-risk areas and infrastructure to best manage these budgets. So from this perspective, it's necessary for us to do detailed engineering analysis of items and look at things like watershed areas, drainage patterns, seasonal projected runoff events, etc. So in summary, we undertook this assessment to undertake a study and provide us with recommendations for infrastructure upgrade, modernization, and to basically increase resiliency and adaptability for future highway operations and maintenance based on climate impacts. So from that point, I'd like to hand this over to Gary. Now you can see his slides up there. Tetra Tech did this study for us, and we look forward to continuing on in the future. So Gary, over to you.
Thank you. Can you hear me?
Yes.
Okay. This is the name of the project, the Infrastructure Vulnerability and Risk Assessment. and we call it the VRA for short. So during this presentation, you'll see that acronym quite a bit instead of saying infrastructure vulnerability and risk assessment all the time. Now, this is an outline of the presentation. We'll start with explaining our analysis concept, which was based on risk-based assessment developed for infrastructure developed by the U.S. Army Corps of Engineers and published in 2011. That assessment did not include climate adaptation, but it did lay out a methodology for monetizing risk and determining probabilities of failure. To do the climate vulnerability assessment, we adopted this FHWA framework, which was published in 2017. And I'll show you what that looks like. And then we'll step through that framework, showing how we applied it to the project, and touch on some applicability to other transportation infrastructure assets. So this is the concept here, that the benefit that you get from adding resiliency must justify the cost of the adaptation, right? So if the benefit, and in this case, the benefit is the reduction in risk by adding resiliency, if that benefit is monetized, if you can calculate how much monetary benefit you get, and if that outweighs the cost of the adaptation, then it's worth doing. This method was chosen because, well, because it makes sense, but also because this is the way that Public Works has been managing the Alaska Highway for some time now. All of the assets and all the improvements along the highway, including geometric improvements and safety improvements and so forth, were all evaluated by this methodology in turn to be used to decide where first to and best to spend money maintaining and improving the highway. So the concept here, and this is a very much asset management based concept. Assets independent of climate were always managed based on a probability of failure or unsatisfactory performance based on the deterioration of the assets over time. And that multiplied by the cost of the consequence of this failure was the risk. So, and that concept was developed by the U.S. Corps of Engineers. But we added to this the increasing probability of failure due to climate events. So that's what the VRA project was about. It was about this monetizing the risks. So the U.S. Army Corps of Engineers, and this is the document that you can Google this if you want and see how it's done, has the concept that over time, an asset, its performance or reliability decreases, and eventually it's going to, the probability that it's going to fail will equal 1, right? It's going to fail, right? And the methodology for calculating this for virtually any asset is published in that document. So for this study, the VRA study, we adopted this federal highway framework, and you can Google that and get how that works. But essentially, it's a step-by-step process to get through the analysis. Now, the first 2 steps of this were defined by the terms of reference of this project. We had a bunch, or Public Works had a bunch of historical data on the highway since they've been managing it for decades. And the terms of reference defined that this particular study would be studying drainage and geotechnical assets. So we'll step through the steps 3, 4, 5, and 6, because the first two were already done for us. So step 3 was obtaining the climate data, and it involved a direct download of modeling climate change predictions to 2098 and dividing the highway into 170 grid cells and applying the models to all those cells along the length of the highway. So the 12 climate models most applicable to the region were used, and this resulted in millions of data points along this length of highway, and ultimately into predictions of the change in the various parameters. In this case, we're showing the precipitation annually over the analysis period, which went to 2080. So this step 4 was divided into 2 parts. It was done by 2 separate groups of specialists within our organization, our hydrotechnical group and our geotechnical group. So when I'm describing this, I'll go first through the drainage assets and then move on to the geotechnical assets. So this process for the drainage assets involved dividing the project up into its component watersheds, one for each crossing of the highway, and then finding the current flow conditions, predicting what the flow would be in 2080 based on the climate changes, and then we had a linear annual change in probability of some return period event occurring for each watershed. So these were delineated for 500 bridges and culverts, and this kind of shows in ArcGIS how we were coming up with these watersheds. Now it says 500 bridges and culverts. We were basically only looking at culverts that weren't just equalization culverts. Like, we didn't look at all the little small 600 or 800 millimeter culverts, which were just equalizing the water levels across the road. These were the culverts bigger than 1 meter for the most part, and bridges, of course. So the flow magnitudes were estimated for current and future years at each crossing, for each of a number of different return periods, like these Q100, 200, 500, and 1,000 year return periods, right? So there's a flow for each crossing and for each of those return period events in each year of the 60-year analysis. So we could get a probability of the return period for each year for each culvert and calculate, therefore, a monetized risk in each year. So for each year you didn't improve it, that risk increased. So we summed up the amount of risk for each existing culvert or bridge, and we got the net present value of the risk for the whole 60-year return period, or 60-year analysis period. So for example, on this example culvert, in that period from 2020 to 2080, the probability was increasing from 14% to 27% for an exceedance probability. Okay, now I'll describe a bit about the geotechnical assets. Now, some of you probably from Parks Canada will recognize this as the Eastgate slide. This is not obviously on the Alaska Highway. I just put this up here because this is one of the early examples of where we applied this U.S. Army Corps of Engineering studies to a geotechnical asset. Total of 74 geotechnical assets were identified based on historical information, imagery, and published data and other studies we had along the Alaska Highway. There was 4 types of assets, geotechnical assets looked at: fill and cut slopes, rock slopes, and debris flows. Each asset was assessed for 2 conditions: the present condition, of course, the future condition due to climate change. In this case, the parameters were freeze-thaw cycles, precipitation, and so forth. A lot of this work was done based on expert opinion. We had a group of geotechnical assets that assessed, or geotechnical specialists that assessed each asset, and independently came up with a probability of failure, and then they discussed them and agreed on what the probability, the increased probability or decreased probability of failure would be in the future based on the climate projections. This is Eastgate slide again. Anyway, these stressors are used to assess the future condition of the assets and expressed in terms of percent of change of predicted stressor considered to increase the annual probability of failure. Now for the drainage assets, we considered several adaptation treatments, upgrading the culverts or drainage appliances to accommodate the 100, 200, 500, and 1,000-year floods using open cut and trenchless treatments. Sorry about that phone. Nothing I can do about it from here. And the same with bridge culverts. There was also a replacement for the end of service life due to the effect of age and deterioration of the culvert. So there's 2 things happening at the same time here. The culverts are deteriorating due to age, and the return periods, in most cases, we're getting shorter. For the geotechnical assets, there's a number of adaptation treatments here. I'm not going to read through them all, but for each asset type, there was a different set of treatments that could be looked at. The next part of this was calculating the cost of the consequence. And this is the key part to this. If you know the road's going to be closed, and you can guess how long it's going to be closed for, or if one lane is going to be closed, or if people have to slow down, you can calculate what the cost to the users is. So there's a cost to repair whatever failed, but there's also a cost to all the users of the highway. So there's vehicle operating costs here, like fuel and time delays, right? For going on a detour or waiting for the road to be cleared. There's also the extra costs of the greenhouse gas emitted while people are taking detours or waiting, whatnot. And this can all be calculated. And so we were able to come up with a cost at each site for some unsatisfactory performance, whether it be load rating a bridge, reducing the capacity of the highway to 1 lane, or in worst cases, detouring around the site. And with the Alaska Highway, a detour is an expensive proposition. Now, these are the traffic volumes at each part of the highway, and that's expressed in average annual daily traffic, and percent of that annual average daily traffic that's commercial vehicles. And you can see this traffic on this highway is mostly commercial vehicles. This is the gateway to the north. So this is supplying the north, right? So a very important piece of highway. And the costs of detouring around a failed asset here is enormous. This shows the lengths of some of these detours, right? If there was a road closure somewhere on the Alaska Highway, you would have to detour starting in Edmonton and a completely different route that's 1,900 kilometers versus the 1,500 kilometers that you would have taken to just drive the highway. So big number for consequence of failure. So these were prioritized. Now we know the consequence, we know the probability. So we've got the monetized risk. We have the cost of all the adaptations. So we could do a benefit cost analysis for any of those adaptation options that we looked at for the various return periods. And so anything with a benefit cost there of greater than 1 is justifiable. And some of these, you can see there's one there with a 9, is fairly risky. Now I want to point out that this is a desktop study, so you can't just take these numbers and say, holy, I'm going to go do that one, that culvert that's a 9. You'd have to do some further study to make sure that really is a 9, right? And that we didn't, using just the limited data we have, we didn't miss something. The highest priority, though, are the ones that we know have deterioration problems just due to age, but are also at risk from climate change. But because we have this analysis, you can allocate funding, A, to do more study on if there really is this risk, and B, to make sure that you take the riskiest assets first, right? If you have limited budgets. Now, because on this particular highway, all the rest of the works, including maintaining the pavements, improving for safety like intersections or alignments, or even upgrading the speeds for the highway, like by realigning them, were justified based on the same benefit cost analysis with monetized benefits. So it was very easy then to incorporate the results of this study into the decision making for the highway. So this step 6 is one of the things that's most agencies are finding the most difficult part, which is figuring out an equitable way to incorporate these adaptations for climate into the rest of the general planning for managing the facilities. Now, the methodology, of course, applies to most assets, right? In fact, one of the first times we did this, I think was in 2011 for the Port of Vancouver. It didn't use the climate change part, but it used this monetized benefit cost methodology, right? And I know I read that somebody has applied it to a US airport, somehow monetizing the cost to operations due to unsatisfactory performance. And that's pretty much the end of mine. I'm going to pass this now on to Vincent. Oh, sorry. One last slide here. This was pretty much a Zoom project. So I just wanted to put a picture of all the team members that worked on this. This is what we saw for the whole year while we're working on this, looking at each other through these Zoom meetings and so forth. We'll save the questions until after the other presentations. Thanks. Okay, Vincent.
That was great. Thank you very much, Gary. So let me share my screen now. Okay, can everyone see that?
I can't see it yet.
Not yet, Vincent.
Okay. Not yet. Go back to Zoom. Share.
There we go.
Okay.
Yep, we
Great.
can see it now.
Okay, so on the second presentation, I'm going to talk about a series of transportation risk assessments to climate change we did in Atlantic Canada within the last 1-2 years, and specifically applied to ferry terminals. So that falls under the Transportation Asset Risk Assessment Initiative of the federal government. One of the first series of studies that was done in Atlantic Canada. And we're going to talk about the goals of the project, the selection of the risk assessment tool that we did that was using the PIVC Climate Risk Assessment Tool, and how we adapted the tool to facilitate decision-making specifically for these types of asset, which are specifically quite specific marine infrastructure assets here with ferry terminals. So these are the ferry terminals we're talking about. So 3 routes, one in the Bay of Fundy between St. John, New Brunswick and Digby, Nova Scotia. The other one between Nova Scotia and PEI, Caribou to Wood Islands. And the third one in the Gulf of St. Lawrence between Surrey, PEI and Cap-au-Mur on the Magdalen Islands in Quebec. And
Hi, Vincent.
Yeah.
Sophie, just one quick thing. Can you please go into present mode? We just see a small version of your PowerPoint.
Yeah, I didn't realize that.
No worries. Sorry for interrupting. Thank you. It's good now.
Does that show now? Okay.
Yep.
So the goals were really to assess high-level climate change risks to these ferry facilities. A number of them were on the second half of their lifetime, shall we say. So before planning major upgrades and replacement, it was a really good opportunity to run this climate change risk assessment tool through it. The objectives was to establish priorities for maintenance and upgrades for facilities which had still a decent remaining life cycle, and recommendations for replacement for those where the planning for new infrastructure needs to be started in the near future. So there's one tool that was developed recently in partnership with Engineers Canada, particularly for these types of assessment. It's called the PIVC tool. PIVC stands for Public Infrastructure Engineering Vulnerability Committee. And it's a risk assessment tool, especially designed for climate change risks to infrastructure. So the tool is quite prescriptive in the methodology. It leads us through formal documented process to identify vulnerabilities and resiliency. That tool was derived from standard risk management methodologies tailored to climate change vulnerability. So the data quality and availability is assessed throughout the process, and it's been a proven tool applied across multiple infrastructure case studies across Canada and around the world, actually. And it can handle cases where data or resources can be limited. And one of the advantages of this tool is that it can be tailored to site-specific application. So that the steps are prescriptive, but what you do within the steps can certainly be tailored to the project. So I'll certainly come back to that tailoring of the tool to the projects we had here on hand. So the goal is to define priorities by answering three main questions when it comes to risk. What can happen, like what kind of climate event can lead to an undesirable consequence on the infrastructure? How likely is that to happen? And if it happens, what are the consequences? So it's standard risk assessment methodology. Risk being defined by the possibility of an injury, loss, or negative impact created by a hazard, in our case, a climate hazard. So the risk being defined by probability of a negative event above a certain threshold times the severity of that event given that it has happened. So we really need to define appropriate climate thresholds and severity, and that comes from a stakeholder workshop for which we held for each of the sites. And it's really important to have the right people in attendance, if possible with previous briefing on climate change, so they can be prepared to discuss. So one of the key things here I highlighted in this slide is that the probability above a certain threshold. So the definition of an actual threshold of concern is one of the key things that needs to come out of the risk assessment workshop there. And then the way it works is that the risks can be ranked on a matrix. So risk being probability of occurrence times consequence. For example, let's say a flood, which could have a very low probability of occurrence, but very negative consequences. In our case, we're on the Atlantic seaboard. So with sea level rise, the probability of infrastructure being flooded will increase with climate change because of rising waters. So that means your total flood risk number goes up. And the idea of climate adaptation is to reduce the consequence by, for example, raising the infrastructure. So that's the whole idea, and that's where we want these studies to lead, is to provide the data necessary for adaptation. So the work plan as defined in the PIVC methodology starts with basic data gathering on the site infrastructure and then on the climate. So it's important to start getting these climate projections sorted out before the first workshop with operators, because at the first workshop, that's where really we get a lot of the insights and site-specific information on what certain climate parameters mean for the infrastructure. So there's always some preliminary investigation as to what the engineering team think the climate interaction should be, but that's always confirmed and refined during the site workshop. And then once we have the data from the workshop, notably on climate threshold and severity values, then we can go back within the team and conduct the structural and operational vulnerability assessments. In this particular study, the cost estimates were not part of the scope, but as was mentioned here with the previous presentation, it's certainly an important decision factor going forward. So that would have been the next step after these studies, is to do the cost estimating. So the climate factors that we're concerned with these ferry terminals are, of course, coastal nature, like storm surges and wave action, sea level, but also wind. So wind is extremely important because it's one of the factors that decide whether a ferry is going to leave dock or not. The operators mostly look at wind forecast because the wind speed will give them an idea of the wave climate out there as well. So wind is a really important proxy and threshold for these ferry operations. And of course, these climate components will interact with your wharves and a vehicle loading bridge and breakwaters and all the marine infrastructure that's at the ferry terminal. So I'll show that on the next slide. This is a typical example at Digby in Nova Scotia. So one of the main components, assume you get there as a ferry user, so you would park your car in the marshalling yard and then wait for the ferry to begin loading. And once you load, the cars drive on the loading bridge. So that's sort of the steel truss structure that you see on one of the pictures there. And sometimes people can wait in the terminal building or buy tickets there. So these are all the infrastructure components that we looked at on a very high level. There's the hydraulic and electrical building control tower as well. That's very important to operate the loading bridge, especially in sites like Digby on the Bay of Fundy that have a high tidal range. The mechanical electrical components are very important as well. So all these have different remaining service lives, and you will see that the remaining service life is an extremely important component in the risk assessment, because that determines whether or not any immediate action is required. So in the climate analysis for these types of PIVC study, we need a good understanding of what local processes are going on from an atmospheric and coastal standpoint. Also have a plan for managing uncertainty, because with climate projections, you have various kinds of uncertainty and variability. So that can be between the emissions scenario, low to high emissions, between climate models themselves, or within each climate model. So it's really important to use multiple data sources and an ensemble of model rather than one particular climate projection. So the key is to account for that variability in the assignment of probability scores in the methodology. So I'm not going to go over all the climate projections, but from high confidence to low confidence, when we look at the different regions here between Bay of Fundy and Gulf of St. Lawrence, we can say that the temperature is going up with climate change, depending on this, more or less depending on the emission scenario. With a little less confidence, we have some idea that there might be changes in wave action, sediment mobilization, but of course the big one is sea level rise and extreme water levels. So that the probability of extreme storm surge events is definitely going up. With the added coastal risk component in the Gulf of St. Lawrence, that there's going to be less sea ice. So that also means more sediment mobilization in the winter and more wave action in the winter. And finally, precipitation that going up as well, with somewhat less certainty than other parameters. Certain sites are expected to see more freezing rain, higher precipitation intensity. The one factor that's really important to ferry operations, but that has very little certainty, is wind. Climate projections with winds show a lot of variability and uncertainty. Some studies show possible increases in wind gusts and changes in direction. On a qualitative level, we can say that warming would favor conditions conducive to hurricanes and higher wind events, but it's very hard to quantify. But that needs to be accounted for in the risk assessment as well, saying that it's a possibility, but it's hard to put a number on it. So how we adapted the PIVC scoring to project. In the original PIVC template that they provide for various projects, the focus is put on the structural soundness, for example, bridges with return periods of 100 to 1,000 years and things like that. What we found for the ferry terminals is that most of the concerns were operational in nature, meaning how often are we going, or how much of an increase are we going to see in wind or in storm surges, because that will determine the amount of ferry cancellations that they have. So we shifted the probability scale to have more frequent event in the higher scores there. For example, near certain, probably, likely, we use daily, weekly, and monthly, because we wanted to make sure that, especially after the workshop, the operators were comfortable that we were including concerns that were recurring at their site. A limitation there of the PIVC tool is that the severity may increase with the level of threshold exceedance. In other words, you could have a 1-foot flood, which could be cleaned up in a reasonable amount of time, but if the flood is 1 meter or 1.5 meters, it could be catastrophic. So that's a difficulty that needed to be dealt with on some level. So I'll show some examples of that in later slides. So the big one is sea level rise in terms of defining future coastal risks. So this is a graph that shows the range of sea level rise scenarios depending on emission scenarios and climate projections. So in the basic PIVC methodology, what's prescriptive is that the assessor will use a baseline climate and the future climate. So of course, what's upon the assessment team is to actually define time horizons. So for this particular study, we used 4 time horizons, which was baseline 20 years, 50 years, and 100 years, meaning that the projections and the probability numbers needed to also reflect the increasing uncertainty in these projections. So as mentioned in the previous slide, the risk is the result of the probability times the severity. So for each infrastructure asset, we developed these risk matrices, which were essentially interaction of climate parameters versus infrastructure component. And once you summarize that in the summary table, such as the one to the right, you end up with a list of assets and a list of risk rankings on a scale of 0 to 49, because probability is 0 to 7 and severity is 0 to 7. So that's that results in the risk ranking number that we have here on the right. And as you can see, with the red being the higher risk numbers, the factors of most concern for this infrastructure are winds, which is wind risk to the ferry service, especially in the fall there, with the winds increasing, and the coastal flooding, extreme sea level, especially on the hydraulic buildings, which are close to the wharf and the ramp, because the ramp will operate only at a certain tide range. We have some slides later on to illustrate that. So that PIVC methodology really allows to quickly prioritize action and areas of concern based on ranked risks. So these kinds of tables were produced for all the ferry terminals, and I'll show some examples of how they compare in the end. So one of the difficulties with climate risk is that we're dealing with non-stationary processes. So it's hard to define a probability in the future because the event is non-stationary. So for example, with sea level rise, if you look at the cumulative probability of over a 50-year lifetime, that probability curve will be greater once you include sea level rise. So the idea of relying on, say, the 100-year event in 50 years is rendered invalid by these non-stationary processes. So we try to introduce this concept of cumulative probability over a given lifetime. And I'll illustrate that with these flood levels. So what you have here is an example of coastal flood mapping. So that's at the Wood Islands Ferry Terminal in PEI. To be able to communicate future risks, even when historical conditions have been manageable, we found that this was a valuable tool. So what you have here in these flood risks is not the say the 100-year flood that will be the 100-year flood in 50 years, because it's a bit of a more abstract concept, but we introduced the concept of 50% cumulative probability level between today and a future state. So that's a tool for communicating flood risk, and we used that during the workshops, which was quite powerful in communicating risk and to be able to better define the severity with the local stakeholders. When we compare that over the next 100 years across all the different sites, and we compare the probability level, so it's quite interesting to see the different sites. And again, this is a ranked system that allows to prioritize which ones are the low-lying sites and which ones should be raised first. So the immediate takeaway from here is that under baseline conditions, so shown as 2018 here, that the probability is relatively low of flooding, but it starts increasing rapidly after the next 20 to 50 years. And of course, within 2120, we have very high probabilities, but by then all the infrastructure will have been replaced anyway. We did similar analysis for downtime for the vehicle loading bridge. The idea here is that the loading bridge for these ferry terminals is designed for a certain tidal range and mean water level. So the ramp is designed to operate between a low tide and a high tide. But what happens with sea level rise is that all of a sudden you might have your ramp on the highest setting there that may not be able to accommodate the high tide. So that's what we defined as downtime. We did calculations on that for the different sites. So that, for example, that's for Digby at the Bay of Fundy. The tidal range there is 9.1 meters, which is huge. So the sea level rise is a relatively moderate portion of the tidal range, which means that the significant decrease in usability will only come towards the end of the century, and we're only talking about a decrease in usability of between 5 and 30% for the worst case sea level rise scenario, and that's only at the very end of the century, and that's assuming constant infrastructure elevation similar to present. In reality, the infrastructure will reach the end of its service life well before then, so there's time to plan. If we compare that with the Gulf of St. Lawrence, where the tidal range is only 2.3 meters, sea level rise is a much greater proportion of the tidal range. So that's where you see the percent usability dropping a lot faster for these sites, because there's less excursion or amplitude for the loading bridge to operate at. But again, this is assuming constant infrastructure elevation similar to present. So what's important at the end of the day is to look at remaining service life. So here's a first look at the Bay of Fundy sites. So we looked at the ramp downtime for Digby and St. John. The remaining life of the ramp is 15 to 20 years, and the frequency of exceedance of the baseline high tide over that remaining service life is quite low, only 11 hours per season, which is completely manageable. Similarly, the flood probabilities for the marshalling yard and the terminal building over the remaining service life, which is between 5 and 10 years, is quite low. So that there's no cause for alarm at these sites. When you compare that to the Gulf of St. Lawrence site, where the tidal range is much smaller, there is a bit more of a concern for these area when we look at remaining service life. So that kind of analysis allows the owners in Transport Canada to more effectively plan which of these ferry terminals should be upgraded and which infrastructure should be replaced at the end of the remaining service life. So based on these downtime analysis and risk over the remaining service life, also well into the future to the end of the century, we developed these asset action plans, essentially producing one sheet per asset. For example, this is the ferry marshalling yard at one of the ferry terminals there. So it's defining the key characteristics of the asset, construction year, age, remaining service life. What are the climate risks as identified by the PIVC methodology? And what would be our recommendations for the maintenance of the existing asset over the remaining service life, and for the design and siting of the replacement asset. So this system of asset action plans allows the client to quickly go through all the different assets and visualize which are in more urgent need of action and what should be planned for the whole range of assets throughout the site. What we learned from these different projects is that right now, coastal flooding and winds are causing most of the concern because they end up causing service delays and interruptions. The worst long-term climate impacts to hit will hit after the end of the remaining service life for most assets. So there's definitely time to plan, and these studies are an important building block in the planning for the replacement of this infrastructure. And the future requirements will depend not only on climate parameters, but also on the new boats and the demand for ferry service and specification of future vessels. So that's a really important element to include in the planning that wasn't in the specific scope of these climate studies. So the studies lay out time horizons and priorities based on climate risks, horizon versus infrastructure service life. Costing was not included in the scope, but the reports present information expected to be useful in future cost-benefit analysis. So the next step would include more detailed engineering to allow high-level costing for capital planning. For next Terra projects, what we would suggest is to continue adapting the PIVC risk assessment protocol to really suit the project. So in our case, we did multiple time horizons, including we included the fact that we have non-stationary processes and put a lot of emphasis on remaining service life as well. We think a second workshop would be beneficial because that allows the operator to give some feedback on the contents of the draft reports and to review the risk rankings, finding, and recommendations. The attendees of the second workshop would include stakeholders that are expected to be involved in the implementation of the study recommendations. And also to enhance usability of the report, we included these asset action plans and also other sort of value-added elements there that include renderings of flood scenarios, which are really important for effective communication, and also short-term standalone summaries, because there's a lot of technical information, especially in the climate part, that is useful to summarize in these short bullet point type summaries. So I hope this was useful, and I'm certainly interested in questions and discussion. Si vous avez des questions en français aussi, n'hésitez pas. Merci beaucoup. I will turn it over to the next presenter.
Yes, thank you, Vincent. That was awesome presentation. I'm not sure, I'm just trying to get my slides up here. Can everyone see that?
Yep, we can see it, Megan.
Great. As Sophie mentioned in the beginning, my name is Megan Roach and I'm joining you from the Calgary International Airport. Today, I'm going to be presenting a few slides on the Calgary Airport Authority's climate change risk assessment that was made possible by the Terra grant funding. So I'm going to start with a little background on the project and then go into the project steps and how we developed our framework for each step. And then I'll finish off by talking a bit about how we use this project to create in-house capacity for our organization. So just to provide a bit of context on the project, As an airport, our operations are very weather and climate dependent, and all the infrastructure that we have functions to support those operations. So both our operational procedures and infrastructure is built with certain weather and climate assumptions, which is or was a really big driver for this project. But at the end of the day, we really wanted to provide some tools and information to the organization that support decisions regarding our operations and assets. We wanted to take a really holistic approach to the risk assessment. So we needed that to include all functions of an airport authority, not just the infrastructure. We wanted to include land use, environmental management, our operations, corporate strategy, health and safety, and emergency response are also really important for us as an airport. So we wanted to incorporate that into the risk assessment as well. We decided on 2 deliverables, the first being an updated climate projection for both airports that we operate. So the Calgary Airport Authority operates YYC, which is the Calgary International Airport, but it also operates YBW, which is our Springbank Airport. It's a regional airport just outside the city limits. Our second deliverable, we needed a preliminary risk registry, and we needed that to help inform airport decisions and provide meaning and context to airport decisions. So we really wanted our risk assessment to prioritize actions and resource allocations to address the climate change, the changes in climate change hazards. So again, we're really focusing on the incremental change in a climate hazard and not the climate hazard itself. If I could give an example, I would say lightning in Calgary is a very common occurrence, especially in the summertime. So we're not focusing on the current event, but we're focusing on the incremental change in those lightning events and what that's going to look like and what that's going to mean for our airport. So we followed an ISO 14001 risk assessment, risk management approach to coming up with these basic steps to our risk assessment. We also used ACROS, which I'm going to get into a little bit later, to kind of provide input into this assessment as well. The airport has gotten as far as step 5. Due to the COVID-19 pandemic, this caused significant delays in getting to step 6, but we are planning to get there this year. So we only got to the risk scoring and analysis. But it's important to note that there wasn't really one framework that we felt fit all of these steps. So I'm just going to go through the steps and talk about how we use the framework and the decisions we made for each one. So we use the ACROS framework, which stands for Airport Climate Risk Operational Screening. It was developed by the United States Transportation Research Board. This graphic comes from an ACRP document. ACRP is the Airport Cooperative Research Program, and it explains the kind of how the ACROS framework works and how it can be used. So what it is they took their framework and they put it into this one-stop shop tool that will give you climate projections, an inventory list. It helps you define asset vulnerabilities. And in the end, it spits out this, really high-level risk screening matrix that you can see in the lower right-hand corner of your screen. Now, this is a really simplified version of the final result. It's just to give you an idea of how the tool and framework kind of functions. Not every aspect of the ACROS tool worked for us. So what we had to do was make some decisions on how we were going to make it work for us. So I've summarized the ACROS tool and the ACROS framework into 4 steps here. The first step, you start by selecting a location. And by doing that, you thereby are selecting regional climate projections that are pre-populated into the system. The second step, you select your assets and operations from again, another pre-populated list, but it was a very comprehensive list. And this list was great because it was very specific to what occurs at an airport. Now, if you're not an airport, I think it could be translated to similar industries like a harbor or a seaport as well. But based on just that list alone, it was very airport specific. Now, based on the assets and operations that you choose, that would really define, from there, you would really define the criticality and the vulnerability of that system. And the tool takes you through all of those processes. And that's really step 3 and 4 on this graph or this slide. So right off the bat, the first step didn't really work for us at all, although the step worked, the tool didn't. So we are a Canadian airport and we exist kind of outside the scope of the ACROS tool, as the tool is based in the US and it has only climate projections for the US, which is totally fine. We knew from the beginning that we wanted to do our climate projections regardless of the capability of the ACROS system. So we have a really great relationship with the city of Calgary, being that we're an inner city airport. And they were also looking to update their climate projections. So this was a really great synergy between the two companies. Together, we decided to contract GHD to conduct those projections for us using both airport weather stations. So we got data from our YYC, the Calgary Airport, and YBW, our Springbank Regional Airport. What we also wanted to do was use our own enterprise risk framework instead of the ACROS tool one, because we felt our internal framework does a really good job of capturing our risk and our vulnerability in a more specific manner than the ACROS tool could. And I'll go into a bit of detail on that later. So our first step was to create an inventory of airport-owned assets and operations. This really helped us define the scope of the project, which is a very important first step as well. It helped us understand what we wanted to include and why. The scope of a climate change risk assessment can get very large very quickly. So defining that right off the bat can save you a lot of time and a lot of headaches in the future. We used, again, we used the ACROS framework, an ACROS tool, but we also used our own documentation and systems like our SOPs, maintenance and incident record systems, and we use those to populate the inventory as well. So didn't just rely on one tool, we used multiple databases and systems to populate that list. There's pros and cons to using any framework. What we liked about the ACROS system is that it is airport specific. It really included operations in the inventory as well. So it wasn't just looking at our built infrastructure, it was looking at how our operations and our people will be affected by climate change hazards. It was also really easy to use and understand. It's a pretty foolproof system. If you want to use a system from beginning to end without any other inputs, you would end up with a pretty comprehensive high-level risk screening analysis. What we didn't like was, again, that it was US based. So our Canadian airport didn't quite fit into the structure. And it didn't account for other functions of an airport authority. So it really assumed the most basic function of an airport, which is, processing passengers and processing planes, and that was about it. But as an airport authority, we do so much more. And I use the example of land use and development is part of our organization responsibility. So it didn't incorporate that, and we had to do that ourselves. It also had very generic categorization. And I think this, applies to a lot of risk assessments out there. I think it's just something you have to handle and deal with. Some of the categories in the operations and the asset list, and also the climate thresholds and impacts, there was some you had to break out, and then there was some you had to lump together because you really felt they went together well. So I don't know if that's, you know, ACRO specific or if it's just risk assessment specific. So step 2 of the climate risk assessment was researching climate impacts and the thresholds of each of those impacts. Again, ACROS was a really good starting off point. It has a large list of climate impacts that were applicable to our airport, but we also supplemented that with our own literature review, information from nearby municipalities like Calgary and Edmonton. We conducted our own internal workshops with YYC subject matter experts, or SMEs as we like to call them. And then we also incorporated some established weather thresholds as well. So our third step in the process was getting updated climate projections for both the Calgary Airport and the Springbank Airport. Again, we partnered with the City of Calgary. The data that that was provided to us will be used in airport projects as well as city and planning and design. So this really creates a common ground between the city's climate risk assessment and our own, which is it's really great level playing ground that we need to be on. One of the most important things we did in developing the climate projections was making sure we characterize the uncertainty, which we will use to better inform our risk assessment. And I'll get into that just a little bit later. I'm not going to go into too much detail, but this table lists just the basic time series that we use for our climate projections. And this is an example of the projections we received. So as I mentioned before, we really tried to characterize the uncertainty in a robust way to better inform the risk assessment. So the graph on the right, you can see the projection, but you can also see in the range of uncertainty of that projection, which will be important later on in our risk assessment. The fourth step was validating and collecting feedback from our initial findings. We did this by conducting workshops and interviews with our internal stakeholders and subject matter experts. We found the easiest and most engaging way to do this was to conduct kind of a World Cafe type event. This is where we had teams of stakeholders walking around, looking at posters and discussing those thresholds and impacts of potential climate hazards. And I have on the slide just an example of the posters that we had posted up around the room to collect feedback. We also prompted them with a few questions like, does this information seem accurate? Can you think of how these impacts could affect YYC and YBW, our Springbank Airport as well? And finally, our last step was to do some risk scoring and analysis. So as I mentioned before, we used our own enterprise risk framework to complete this step. The criteria in the framework includes likelihood, cost, regulatory and environment implications, health and safety, reputation or image, passenger traffic, and business continuity. Now, we chose our internal framework for this step because, as you can see from the criteria, it has already been tailored to our organization. We wanted to have that continuity with other risk assessments across the company so it could be evenly compared with other risk assessments. What's also important to note is that our risk scoring includes a factor related to the overall confidence in the information. So this really goes back to the uncertainty that we captured in the climate projections. We brought that into the climate risk assessment. This is, the climate risk scoring. This is where we currently are in the risk assessment. So we've done some initial validations of our findings, but the process is still ongoing. And the next step, of course, would be to create some risk treatment recommendations. Finally, I just wanted to touch on a unique aspect of our Terra project, and that is that we hired and created and conducted this risk assessment in-house, which was a bit different from other Terra projects in Terra, I believe. So there's some pros and cons no matter which route you take, but for us, we found the pros to be continued climate risk support for the organization. We had more control and insight into the project and kind of steering the project to where we wanted it to go. There was more continuity in incorporating climate change decisions over the longer term. And then we also found that we really built the competency in-house, not just with individuals, but across the organization, and not just with climate change, but in risk assessments in general. The cons, we found that the process was a lot slower. The learning curve was quite steep, especially in the beginning, and that we had to overcome. And we found that the team was sidetracked into other projects and assessments. Just as the organization priorities changed, you were kind of pulled in different directions. And you don't have to fully choose one way or the other. You don't have to do everything in-house. You don't have to have everything contracted out. You could do a mix of both. In our project, for example, we contracted out the climate projections, but that's basically because we just don't have the capacity to do that. Everything else we kept in-house. So I wanted to just say thank you to Sophie and Suzanne and Michael and the entire Terra team for putting this together. And yeah, that's it for me.
Thank you, Megan, and thank you again, Gary and Vincent, for your excellent presentations. You each helped demonstrate how established climate risk assessment tools and frameworks have been put into practice by respective Terra-funded projects and how they've been adapted to your needs. So now it is time for the question and answer period of our webinar. To those who have posed questions through the chat box, thank you for your submissions, and we will now try to answer as many as possible. If anyone else has any questions, please enter them into the chat box at this time. Should you wish to pose your questions verbally, please use the raised hand function by clicking on reactions, which can be found at the bottom right of your screen, and by selecting raise hand, and wait for us to call upon you and/or mute you. Again, if you're experiencing any technical difficulties, please message Suzanne Sealing. Although we greatly appreciate all the chat box submissions, given today's focus on climate change adaptation, we will not be addressing those related to mitigation during today's Q&A period. On that account, to get us started, we will begin with adaptation-related questions which we received through the webinar registration page, and I will go in order of the presentations today, starting with Gary. So Gary, one of the questions received was about whether different engineering-related climate parameters, for example, snow and ice accumulations, can be forecasted and analyzed for a variety of applicable engineering applications.
Okay, we've got our climate guru on the line here, Albert Leong. Albert, maybe you want to answer that one. Are you there?
Yes, I'm here. Can you guys hear me?
Yep.
Great. Yeah. Well, I mean, there is definitely limitations on what kind of forecast you can look at. That's one of the things. I mean, we were limited by the outputs from the global circulation model, right? I mean, the global circulation model's output include precipitations, air temperature. Of course, air temperature, it's daily air temperature and wind and stuff. But from these basic model output, you could derive all kind of different parameters, such as what is the free thaw cycle. You just by inferring to the result, right? You know how often it crosses the freezing point, right? Then you can derive, okay, how what's the free thaw cycle? What's the frequency of that? You can derive all that, right, from that basic parameters. And what's important to engineering, to a particular engineering project, such as a geotechnical, or like let's say this highway project, right? There are a lot of geotechnical aspect to it, and you definitely have to look at Maybe sometimes you have to look at how fast the air temperature fall, right? The rate of falling of the temperature. You know, I'm not really exactly the expert in, you know, what dictate the SWOT engineering aspect of it, you know, but we could, you know, when an engineer tells me, okay, I need certain climate sort of parameters, right? Like I said, like how often it's free or thaw and thaw, right? Then I can, we can you know, digest the data and create that trend from it. So a short answer is yes, but definitely still limited by the model's output from the global circulation model that we use. Yeah. Hopefully I answered your question.
Yes, absolutely. Thank you both for your response. We also got one more question in the chat box for Gary, and that was asking about the range of expected increased runoff across the highway and the time frames. And the question asked, would you say whether there's some average rule of thumb for, say, year 2100? I've heard plus 15 for the Vancouver area. Do you have any thoughts on that question?
No, although I suppose you could come up with something like that. What we were looking at was the probabilities of the occurrence of a given return period, say the 500-year rainfall event or whatever, and getting the probability, which would be 1 in 500 years, of that event, and then what would that event be, right? So that's what we established for each thing. We didn't look at what would be an average prediction of increase in say rainfall, because the location is so big and it goes through so many sort of different little cells of climate that there isn't really an average for the whole highway. Does that answer the question?
Yep, I think so. Thank you for that. So perhaps now, for the sake of time, we shall move on to Vincent, the second presentation. So there was a question in the chat box about how to explain the cumulative probability. And so for the 2040 map, for example, what does it mean if there's a point underwater, whereas it isn't underwater for the 2020 map?
Yeah, so that's a great question. That's essentially the 50% probability level. So if it's the 2020 map, it's a 50% probability level that you will see this area flooded during the year. So it's the 50% chance. And then the time horizon defines up until when. So for example, if it's 2040, it's a 50% chance that this area will be flooded at least once between now and 2040.
Thank you, Vincent. I'll move on to one other question from the chat box that was also linked to a question received during the webinar registration, and this one will be for Megan. And so the question is, how do you decide which framework to use for your project? And then linking up with the question from the chat box is, how do you get permission to use the various frameworks that were discussed? And is there a user fee or a need to purchase access?
Yeah, that's a really good question. You know, we talked about why we picked the framework that we did, but we didn't really talk about how. It was a bit of a discussion about from the team for quite a while, because we really wanted to pick the right framework. So it started by looking at all the frameworks. We did look at PIVC, and we looked at a bunch of other frameworks and how that could fit our organization. And we really decided where we were lacking was in an inventory list, and what we were really looking for was an airport-specific model, which we found in the ACROS framework. So that's how we decided on that. As for the second question, that is a very good question, and I'm not sure I know the answer. Actually, we have access to the ACROS system. I'm not sure if we're a member of that organization, the ACRP. So I can look into that and get back to you for sure on that.
Great, thank you, Megan. I'm wondering if either Gary or Vincent would like to add, given the range of tools and frameworks that you use. So you can either comment on how you decided which framework to use for your project and also on the permissions if you would like to do so.
Sure, I'll go first. Public Works did a bunch of research before the start of the project and found this FHWA publication. And it's a publication and it's public. So it's not like there's any cost to trying to use the framework, right? The US Corps of Engineering one is also a published document, so there's no cost to looking at how it's done, right? In terms of actually doing it, there's some software and whatnot involved, some pretty sophisticated software, in fact, to do this multi-strategy lifecycle cost analysis. And there might be some cost to that if you don't already have that software. Does that answer the question?
Absolutely, thank you. Vincent, do you have anything you'd like to add?
Yeah, just simply the risk assessment frameworks are generally provided they can be tailored to different industries. So for example, the PIVC one we used was specifically tailored for infrastructure. But some others, for example, can be tailored to water infrastructure, or so there are different ones out there, and a lot of them rely on the same principles, but it's certainly worth it to have a look at the differences between and to which particular fields of application they were tailored to.
Thank you, Vincent. That was really helpful. So our last question today is a question received from the webinar registration page, and it's for Michael. And so that was somebody who was asking about the general key lessons learned gained from the administration of TERA projects from a TERA policy point of view, if you have anything to share.
Oh, thanks, Sophie. I'm just trying to turn my video on. There we go. So this was a really great question. I did think about it a little beforehand because Sophie did let me know this was asked. There have been lots of really important lessons learned that we've heard from our project partners. One really important one which we've tried to tackle through hosting this webinar is making sure that the climate risk assessment tool or framework that a given project uses is a good fit for that asset, considering the asset's size, mode, and broader geographical context. But other really important lessons learned would include things like involving the operators of an asset in the risk assessment process, not just desk workers or consultants, choosing RCPs for climate analysis that fit with the overall capitalization plan of an asset. So you're not making climate projections for things beyond a point which you will be rebuilding or taking major retrofitting work either way. Also really important and an increasing focus for us at Transport Canada, I would say, is considering climate risks not only to the built infrastructure of an asset in isolation, but also to the way that an asset is operated. So for example, that would include things like what do changing weather patterns mean for outside workers or vehicle movement through an asset? And also climate risks to the broader transportation network within which an asset is situated. So, even if a given port, for example, is relatively climate resilient, the rail network that it draws from may not be, or the other ports that ships are heading to from there may not be resilient either. There are overall a lot of lessons learned that we've had the chance to hear from our project partners. And if anyone does have any specific questions or interest in just a broad overview of those, they can definitely feel free to reach out to me and I'll be happy to share some information.
Thanks, Michael. And on that note, I hope everyone enjoyed today's webinar. I'd like to thank our presenters once again for their time and efforts today, as well as our audience and our attendees for your participation. I would additionally like to thank my colleagues from the Climate Change Adaptation and Planning team and Suzanne Sealing from the Climate Risk Institute for helping organize today's webinar.